So this is day 5 on topic 1 of our cornerstone review, and we're writing equations of lines. Write the equation of each of the lines in slope-intercept form, then graph the line. Okay, so example 1, we have these 2 points. I can graph the line right now. -1, 3, there's a point. 2, 4, there's a point. And with 2 points, I can graph the line. Usually I want more than 2 points just so I can feel like my line isn't too swervy or anything. So I'm going to hold off on graphing this, but I know it's going to look something kind of like this. Right? It's going to go through those 2 points. But let's actually find the equation so we can be maybe a little more precise with that. Step 1 when you're writing equations of lines and given 2 points is to calculate the slope. We don't have the slope yet. We need to find the slope. Slope, y minus y over x minus x. So I'm going to take 4 minus 3 divided by 2 minus -1. So it looks like this is 1/3 for our slope. And if I look at my graph between these 2 points, up 1 over 3, that looks pretty accurate. So again, step 1, find the slope. Step 2, we're going to go to point slope form. I could use either one of those points. They're both using small numbers. I like that. This one uses positive numbers. Usually I prefer that. So with point slope form, I have y minus 4 equals our slope of 1/3 times x minus 2. So there's point slope form. They want us to get this into slope-intercept form, so this isn't it yet. We need to do some algebra to manipulate this around to get it into slope-intercept. So I'll pause for a second. Can you distribute? Can you move things around? Can you combine like terms? So 1/3 needs to distribute. So from red to green, we have this. This is a little bit closer to slope-intercept form. One more step. +4, we have to get the 4 off the left side. If you want to use your calculator, by all means do that. -2/3 plus 4. I think that's going to come out to 10 over 3. So y equals 1/3 x plus 10/3. 10 over 3, same thing as 3 and 1/3. So here's my equation in slope-intercept form. This gray equation is equivalent to that gray equation. They're just in a different form. It's like calling the same person by 2 different names. They're one name, their nickname, maybe they have another nickname. They are the same thing, just a different form. So from here, 1/3 x plus 10/3. I look at the first 2 points I have. It looks like the slope was up 1 over 3. So I can do that again, up 1 over 1, 2, 3, to give myself another point, up 1 over 1, 3, another point. They're all lining up nicely. There's my graph. If I was going to try to graph from this and put my y-intercept at 3 and 1/3, that would be really approximating it. And if I really zoom in on my graph, which is hard to see, like this is 3 and 1/3. There's no way I'd look at this graph and say, aha, clearly that's 3 and 1/3. That's why using those original points probably is a little better idea than trying to graph from this form. So equation of line, find the slope, point slope it to get it into slope-intercept form. Number 2, write the equation of the line in slope-intercept form of a line that is parallel to this one and passes through that point. So yesterday we talked about parallel and perpendicular. If 2 lines are parallel to each other, that means that their slopes are equal. So because it's parallel to this one, it means the slope of the line that we're supposed to write is also equal to 2. I'm going to pause for a moment again. Can you write the equation of the line that goes through this point, uses this slope, and write it in point slope form? y minus 6 is equal to the slope of 2 times x minus this x value of 2. So there's point slope form. If you have that, can you do the algebra to get it into slope intercept form? Distribute, move around, combine like terms, take it from point slope because we want in slope intercept. So y equals 2x plus 2. I like this equation a lot because of the integers. The y-intercept is 2. Slope is up 2 over 1, up 2 over 1, up 2 over 1. There's my line. It was supposed to pass through the point 2 comma 6, so I can make a quick check. 2 comma 6, there it is. Feeling pretty good about my answer. So this is kind of a continuation off of yesterday's with writing equations of lines. There are some special cases, and numbers 3 and 4 are some of the special ones. We're still trying to write the equation of the line. Now it passes through these 2 points. And before I start doing all of my calculations, let's go ahead and graph this one first, because as I'm looking at these, I noticed something pretty specific about this one. The first point is 7, negative 9. So right there. And the other one is 7 comma 12, which doesn't quite fit on the graph, but I can kind of make it fit. Over 7 up 10, 11, 12. And now if I'm going to combine these 2 points into one line, the line is going to look like this. And that is a special case. That is a vertical line going straight up and down. And as I start looking at all the points that are on this line, 7, 0, 7, negative 1, 7, negative 2, 7, negative 3, or above, 7, comma 2, 7, comma 5, 7, comma 9. All of these points have one thing in common. They all have an x value equal to 7. So again, these both have the same x value. That's how I knew it was going to be a special case. Every point on this line has x equals 7. Now, if I didn't notice that, I'd go back through my regular process. Calculate the slope, y minus y over x minus x. I have 3 over 0, and that tells me, uh-oh, I can't divide by 0. This is a special case. This slope we would call undefined. Undefined slope is when you have a vertical line, the way you write the equation of an undefined slope line is x equals, and it's x equals 7 in this case. So special case number 1, if the slope is undefined, put the points on there, see if you can kind of logic your way through it. X equals 7 is the equation of this line. X equals 7 for every point on that line. Having seen this one, I want you to look at number 4 and see if you can take yourself through that same process. Look at the points. What do you notice? Graph them. Can you figure out what this equation is going to be? So 12 comma 4 is just barely off the right to the graph. 5 comma 4 is fine. I look at those 2 points, draw the line that connects them, and now we have a horizontal line. Again, another special one. If I were to start putting more and more points in there, start filling it up, every single one of these points has the y value that's the same. Those y values are always 4. Special case. I observed that, and that's how I knew it was different, because these y values were the same. If I didn't, I'd go through my calculating slope, 4 minus 4 divided by 12 minus 5, that is 0 over 7. 0 divided by 7 is 0. Special case. Anytime the slope is 0, it is a horizontal line, and the equation of the line then is y equals whatever x value they have the same. Those are the two special cases. There's day 5. All right, day 6, solving systems of equations, first by graphing. We want to figure out where do these two lines intersect, and we're doing it by graphing, so hopefully, fingers crossed, hopefully their intersection is an integer rather than an ugly fraction or decimal. Step 1, graph that one. Y equals -1/2 x plus 6. Use your graph paper, graph that. And I'm going to put all of my points going from left to right in this one just to make sure that I have a complete picture of this one. Hopefully, the other line hits one of those points. So here's our first one. I'll highlight it in yellow. Here's the second one. I'll highlight it in blue. So do they cross? Do they intersect at one point? Looks like we've got a point right there. That point would be 2, 5. So 2, 5 is our intersection. So why would we use graphing to solve? Well, we'd use it if we are going to get a nice integer point, and it tells exactly what we're doing. So there's our example 1. Solve the system. Where do they intersect? Go ahead and move on to number 2, which is a little bit different in the form we were given. The first one is standard form. We could get this into slope-intercept form. Solve it for y. Might not be a bad idea. So can you do the algebra to solve that one for y? Y equals -2/3 x plus 2. So down 2 over 3, down 2 over 3, down 2 over 3, or up to left 3, up to left 3, one more time, up to left 3, draw my line. There's the first one. The second one is a special case, x equals -3. We just went over one of these not too long ago. What kind of line is this? Vertical line. X equals -3 everywhere, so it's going to go straight up and down vertically. Do they intersect? Yes, they intersect at -3, 4. There's 3 ways to solve systems of equations. This is the first way. Graphing is the least precise because, again, if we're getting a fraction, I wouldn't be able to tell by looking at the graph. In some ways, it is the most concrete. I can see exactly what's going on, but I think the algebraic ways with elimination and substitution are going to be easier, and they will always be more precise. So first of all, substitution. When would you want to use substitution? If I look at these equations, and if in one of the equations there is a single y or a single x, substitution isn't that bad. So in this first equation, y equals 2x plus 1. This one y is solved all by itself. I'm going to circle it and draw an arrow to put it in for y in the other equation. This is my substitution. Y equals this, plug and play. Plug it out of this one and into the other one. So now we can rewrite this bottom equation not as 3x plus y equals -9, but 3x plus 2x plus 1 equals -9. And what we've accomplished is we've taken this second equation And instead of having two different variables in it, now there's only the variable of x in there. And because there's only one variable, we can actually solve this one algebraically. Combine like terms that are on the left. Subtract 1 from both sides. Divide both sides by 5. We have x equals -2. Now, this is supposed to be a point of intersection. Every point has an x value, yes, but it also has to have a y value. So find the y value. You could plug -2 in for this yellow equation and you could get it. Or you could plug it into the blue equation. I'm going to go for the blue one. Plug -2 in for x, so y equals 2 times -2. Again, plug it in for the x. That's -4 plus 1, so y equals -3. Our intersection then is -2, -3. Substitution to solve the system of equations. When do we want to use substitution? If in the two equations, there is one variable that has a coefficient of 1 in front of it. This blue one was already solved for y. It was nice and set up for us. In number 4, I see x in 2 locations. I see y in 2 locations. Which one of these variables, x or y, in which equation, the first one or the second one, should we solve for? Is it going to be the easiest to get by itself? I would say the bottom one for y, right? Because all we have to do to get y by itself is add 3x to both sides. This is what y equals in that bottom equation. Now that we have y by itself, I'm going to circle it. Remind myself, this is what y is equal to. Draw an arrow because it's going to be plugged into that other equation. So now this top equation, the one I have highlighted in yellow, I'm going to rewrite. It's 2x plus 5 instead of y. Here's my substitution. I'm going to plug this in for y. I'm going to plug the 3x plus 10 where that y was written. Everything else in that yellow equation is exactly the same. The great news about this new equation is that there's only one variable. That variable is x. So distribute, combine, subtract, divide. Do what you need to do to solve this equation for x. Thankfully, again, it comes out to an integer. We got some big numbers, but it still came out to x equals -3. Still have to go after that y value, so plug that back into one of the originals. I think this is probably the easiest place. Plug it into this blue one that we solved for. X is -3. Plug that in, we get y equals 1. -3, 1. It works for both of those equations. I could check it. I could plug -3 in for x, plug 1 in for y, and it should work. Plug it in for the other one, it should work as well. And we don't always solve for y. It's just kind of been that way so far. In number 5, we have to ask ourselves, which one of these variables should we solve for and which one of the equations? Which one is closest to being all by itself? First one we could solve for y. And there's a couple of steps to make it happen, but it's not too bad. how about I add y to both sides and add 1 to both sides? Wouldn't we get this? Plus y, plus y, plus 1, plus 1. So y equals 2x plus 1. Right, couple steps, all both in the same step. I smashed them together. This is what y is equal to again. Plug into the other equation. So then this bottom equation, 8x minus 4 times y is 2x plus 1, equals negative 4. Parentheses, super, super important. It says minus 4y. This is all of y. 8x minus 4 is equal to negative 4. 8x minus 8x, they cancel each other out. Negative 4 equals negative 4. Add 4 to both sides, I get 0 equals 0. This is one of those weird cases. I didn't get x equals 3. I didn't get x equals negative 2. I got 0 equals 0. Does 0 equal 0? Yes, all the time, right? So what's happening here? Well, these are really the same line. They're just in different forms to begin with. So where do they intersect? I'm not going to say all real numbers because these don't have all real numbers in them, but they do have infinite solutions. Not every single solution, but there are an infinite number of them. All right, number 6. We have some choices here. In the first equation, it wouldn't be that bad to solve for y. And in the second equation, it wouldn't be bad to solve for y either. I'm going to opt with the second one because all I'd have to do is multiply everything by a negative. And this is what y equals in the second equation. Circle it, bring it up here, and then rewrite that equation. 2x minus parentheses 2x minus 3 is equal to 8. 2x minus 2x plus 3 equals 8. Distribute that negative sign. Once again, these cancel each other out, but now we have 3 equals 8. Does 3 equal 8? Ever? So do these lines intersect ever? For this one, we would say it has no solution. They never intersect. They must be parallel to each other. That's the only way that they would not intersect at all. So the weird cases, the interesting cases, if you get 0 equals 0, infinite solutions. Something that's not true, no solution. Quick recap. Solve systems by graphing. Okay. Not the most precise and is never going to tell us if the answer is a fraction. Substitution. If we have a single x, we have a single y. And now the third method, the one we probably use the most, called elimination. Step 1, step 2, step 3. When would we use this one? Anytime that it's not easy to solve for 1x or 1y. Example 7. If I was going to try to solve this for x, I'd have to deal with some fractions because I'd have to divide by 4. If I was going to try to solve for y, I'd have to divide by 6. I'm working with fractions. I don't particularly want to do that. However, great news here is that the y values are complete opposites of each other. So when we add them together, 6y plus negative 6y, gone, eliminated. Add everything else though, 4x plus 3x would give us 7x, 32 plus 3 gives us 35, and just by adding them together, the y value has been eliminated. And that's what we wanted. Now we have an equation with only one variable, and that variable is x. Divide both sides by 7. X equals 5. Like that, we have x solved for. But we still need y. Plug it in. You could plug it into the top equation. You could plug it into the bottom equation. It doesn't matter. I chose the bottom because smaller numbers. So plug 5 in for x into one of those equations. 5,2. Elimination. There are a lot of tricks in that one. Just do your algebra well. In number 8, I will say there is a little bit of trick in this one. Look at the equations. And intentionally thrown off in this one. Notice how the first one has y first, x second. The second one has x first, y second. That is slightly off. So maybe I could put negative 4y, positive 3x second equals 14. I'm just rearranging this one, putting my y value to match with the y value. It's the only thing I did. But like the previous one, what happens if we just add them together? 4y, negative 4y, poof, eliminate each other out. 3x plus 3x, we're adding, so that is 6x. Don't forget to add the right sides. 22 plus 14 is 36, and we have an equation with only x in it. Divide both sides by 6. 36 divided by 6 is 6, so there's that. Then plug x equals 6 into one of the equations. And we get an intersection at 6, 1. Elimination. X and Y, X and Y. Now we have different letters, R and T. Don't make you think that that's anything different than what we've been doing. Again, they tried to trick us a little bit here. They put it in a little different order. T then R, R then T. Let's go ahead and take this top equation, bring it down here, change the order off it. Also, what do you think we should do to this top one so that when we add, we can get something eliminated? Multiply by negative. So let's multiply everything by negative and change the order. So negative 5R is going to lead it off. Then a negative 2T. Also, don't forget to do the right side. That becomes a negative 6. So this equation multiplied by negative 1, and then R and T changing orders to match up better with the other equation becomes this yellow. So I don't confuse myself too much. Maybe I want to cross this one out then so I know I'm dealing with these bottom two equations. Bottom two equations are set up really nicely now. The T's are complete opposites. Add them, poof, gone. Add your R values. Add the right side. Solve for R. Once you have R, plug it in, solve for T. So plug 4 in for R. 22 minus 36, I believe, is negative 14. Divide by 2. So in this one, it's not x comma y. So I'm not going to put it in an ordered pair. I'm just going to say R equals 4, T equals negative 7, and I can put it like this. If I were to put it in parentheses, alphabetically, R comes before T, so I could do this. Although we usually only do ordered pairs when it's x comma y. So I wouldn't recommend doing it in that way. I'd just say write it like that. To the last one. There's number 10. Let me be quiet, give you a chance to see what you can do on this one, strategize, and then go for it. would say let's multiply this bottom one by a negative, or we could have done the top one. The reason why that's helpful is because now when you add the b's together, they are eliminated. 3c minus 7c, that's negative 4c. 11 minus 7 is 4. Divide both sides by negative 4. C is negative 1. Plug it in, solve for B. I got 14 over 8. I can simplify that to 7 over 4. Still not exactly a pleasant looking answer. And this kind of epitomizes why I would like to do it this way rather than graphing. If I were trying to graph this as like 8x plus 3y equals 11 and 8x plus 7y equals 7, they would intersect at x is 7/4. And if I looked on a graph, there's no way that I'd be able to say, oh, clearly that's 7/4. When you get fractions, graphing is not good, but it is exactly 7 over 4, comma, negative 1, where these would intersect. So there is our solution to this system.